Hi, my name is William Johnson, and I will be presenting the Physics 2211 Lab 4, which deals with oscillations. The goals and results of this lab are the goals are to compare the observed motion of a mass hanging from an oscillating spring via tracker to a computational model via GlowScript, and then plot the energy graphs that occur in the system for the predicted motion. A quick summary of the results of this lab are the predicted motion and observed motion are mostly similar in both axes, with the greatest similarity in the x-axis motion. The change in total energy is zero. The change in other energy is while kinetic energy changes proves this. Newton's second law is a key concept in this lab, as the net force is equal to the change in the momentum or the change in time, and then the velocity update formula along with the position update formula. The energy principle is also extremely important in this lab, as the change in energy of the system is equal to the work done by the surroundings, plus the exchange of thermal energy between the system and the surroundings. A system should be defined when dealing with energy because that affects the energies that are present. And for a system with multiple interacting objects, there's a possibility for the following energies in the system: kinetic energy, spring potential energy, and gravitational potential energy. The system is the Earth, spring, and mass, with nothing in the surroundings. The free body diagram, as you can see, is the force of the spring points upward, and the gravitational force points downward in a static equilibrium position. Here's the tracker analysis for the lab. The spring just oscillates back and forth, and the time and x and y positions are calculated. The object mass, which was given, is 0.402 kilograms, and you can see the start time is 0 seconds, and then the initial plot position and the initial velocity, and then the time of last observation. I inputted for the initial conditions and constants the mass of the ball, the position and velocity of the ball, the gravitational, the acceleration due to gravity, which is just 9.8 meters per second squared, and then the spring constant and the relaxed length of the spring. Here are the equations some of the equations that I inputted. I inputted L hat, which is just L, the vector L divided by the magnitude of L. I inputted the S, which is the L, just the magnitude of L minus L naught. And then I inputted the equation for kinetic energy, gravitational potential energy, and spring potential energy. The force of gravity is just negative mg in the y component, and then the force of the spring is negative k times the magnitude of the vector L minus L naught times L hat. And then the net force is just the sum of the forces. And then I also inputted the velocity and position update formulas. You have to continuously update the variables along with the equations throughout the iteration in the iteration conditions, which is why I changed the kinetic energy, changed kinetic energy, gravitational potential energy, and change in gravitational potential energy, spring potential energy, and the change in spring potential energy. Here are the results of the computational model. Here is the resulting graphs from the computational model. And then here I'm going to discuss those graphs. The change in energy versus time graph, the change in gravitational potential energy, which is in red, and change in spring potential energy, which is in green, are opposite signs that oscillate back and forth. The change in kinetic energy, which is in blue, also oscillates in order to match/offset the potential energy due to the law of conservation of energy, and is in less magnitude than the other energies. The position versus time graphs, the x position versus time graphs is accurate. And the y position versus time graph is not as accurate in relative to the x position. Potential sources of error are not accounting for drag force, failing to pinpoint the exact center of mass, and not accounting for thermal energy or rotational kinetic energy. The energy principle is satisfied. It can be observed in the energy versus time graph that the sum of the change in kinetic energy, the change in gravitational potential energy, and the change in spring potential energy equates to 0. And the oscillation periods based on the x and y positions from tracker, which you can see from the graphs on the right. The time in between one complete cycle is given by the period between two troughs in the position versus time graphs. The x position average oscillation period I calculated to be 1.646 seconds, and the y position average oscillation period I calculated to be 1.488 seconds, which is just the difference of 1.158 seconds. The difference in times of oscillations can affect the spring constant K, which can therefore affect the spring force and spring potential energy. And the difference in periods is most likely caused by drag forces, incorrect center of mass in trackers, or camera errors in tracker.